Continuing from where we left last time, I'm going to talk a bit about some of the responsibilities for being professional engineers, design engineers. Okay, so this is a commonly overlooked thing in education as well as in industry, but it's very important that you know what your responsibilities are as engineers and abide by them. Okay, one of the responsibilities is clearly satisfaction of client needs. Right, and that's kind of obvious. As professional engineers, you need to have good communication skills. That includes not only presentation, but also writing skills. That's because as engineers in a company, you will be required to submit technical reports, sometimes document your work, things like that. And so it's important to be good at writing. Presentations comes when you are trying to convince others that or convey information about what you did and why it should be the way you did it and so on. So we've also seen some other things about design, which I put in that flow chart last time. The different steps of the design, including identification of the need, the problem statement, and so on. You need to go through that if you are designing something, right? See figure on design flow, the last class. Okay, now you probably want to be an active member of your community. So for mechanical engineers, we have active member of your professional community. And for mechanical engineers, that's typically ASME, which is the American Society of Mechanical Engineers. Okay, so for example, I am a member of ASME, and the way I work with ASME is that we publish conferences and journal papers as part of the community. I do that. I review papers, but that is something which you do in academia. If you are in industry, then you probably want to go and attend meetings. One thing which is very common between academia and industry is that one of the goals of ASM is to promote engineering among young students, right? Students who otherwise won't be exposed to engineering and will not take engineering career. So go out in schools and tell what you're doing and what you aspire to do, and then motivate them to pursue engineering. So all those things comes with being a part of ASME, and I highly encourage you to join ASME within the university. So we also have a ASME student section, and I encourage you to join it. I believe they have a lot of outreach activities. They also have clubs where they do different things. So in regards to this, I highly recommend videos, and I'll put some of these videos as homework. There are these outstanding videos by a professor in Purdue. He's a retired professor. His name is Michael Louis. And he has posted a lot of videos on professional responsibilities and ethics in engineering. Okay, I'll talk a little bit about ethics in engineering, and that's, I think, is very important as design engineers. You have to be responsible for what you're doing. Okay, by the way, I'll be posting all this. Like if you've gone to Blackboard, you should have seen I posted lecture notes from last class. I also posted the video which came out from recording this. I'll post that. If you want to write it down, that's fine. If you don't, what is ethics? Well, it's a discipline of dealing with what is good and bad and following one's moral duty and obligations. And one sec. And then we as engineers have to follow certain ethics. Now, every association has its own code of ethics. So ASME, for example, which I think all of us can identify with, has its own code of ethics. So if you search code of ethics, ASME, you'll be redirected to a web page where they'll tell you the code of ethics. And other institutes also have their code of ethics. So civil engineers, there's ASCE. For electrical and electronics engineers, IEEE, and so on. Okay. So for example, you can go and search these things. And as professional who has graduated with a degree in mechanical engineering, you are supposed to follow these ethics. So here's an example from the ASC Code of Ethics. So this is something which you can find if you search. So engineers shall hold paramount the safety, health, and welfare of the public, and shall strive to comply with the principle of sustainable development in the performance of their professional duties. Yes, turn off this light. Okay, so that is one of the many ethics which has been listed in ASC. So give you an example. Let's say that you're a civil engineer, okay, and then you are basically paving the road, okay, and then when you're paving the road, and let's say it's on a bridge, and that bridge has, you notice something on the bridge, something is not right. The question is, are you supposed to go and do something about it? It's not your job to do anything about the structural part of the bridge. You're only paving the road. Should you just ignore it or should you report it? Well, for the code of ethics, you are supposed to think of the safety, health, and welfare of the public. So if you think, and in this case, it's clearly a safety hazard for people who will use this bridge because it can potentially fall down, you are supposed to report that. Okay, now where do you report it? You could go to your boss and say this is going on. Maybe you're working in a government organization which sees the welfare of all the infrastructure, and maybe you need to go there. You need to find the right place and report it. That's very important because as an engineer, it's your moral obligation to report if you think that something is unsafe. Here's another example, and this is maybe more of a mechanical engineering example. On Jan 28, 1986, the astronauts on Challenger were killed 1 minute into flight. Okay, and now this is a serious disaster, right? What happened was basically that the engineers built the Challenger, and they were really not ready to launch it. Okay, there was faulty design. The engineers noticed it. They brought it to the management. The management said, it's okay, we'll just let the Challenger fly off. It turned out that in this case, it was NASA, which is the National Aeronautic and Space Organization, which was sending Challenger. They decided against the warnings of the engineers because they thought that, well, in that time, in 86, I think the conditions were such that Europe was gaining on space age, and so they wanted to send the Challenger as soon as possible. There were a number of times that the Challenger mission was aborted before it was launched. And I believe the president that time, and I forget the name, he was trying to go for a re-election. So there was like this need for launching the missile that way he can come be re-elected. So all these things put pressure on NASA to launch it, and it led to an ultimate disaster. And so this is one of the things where you would not do things, right? Not go ahead with the mission because it's not safe for humans. So that is a moral obligation which the engineers realized. Unfortunately, the administrators did not. Some of the references I have, and I'll post this. I will show you I will assign some of the videos by Michael Liu, and he did a great job of explaining some of the moral responsibilities of engineers. Okay, so Let's move on. The two terms, standards and codes, but really they are two different things. Let's see what standards are first. So standards are basically a set of specification. And those specifications are for parts, materials, or processes. So if you're making a product, what material should you use? What processes should be used to go ahead with the manufacture and so on. Now, the goal of having standards in the industry is to reduce variability, helps to reduce variability. Okay, so let's say that you have an automobile and you want to replace the tire, right? And then you cannot get the original tire, so you go for a different company. Now, if that company followed a different standard, then you will end up with a tire which doesn't meet the specification and you can't use it. So since the variability is reduced, invariably you can reuse something else, which somebody else or a different company made. Now, the standards are typically set by the manufacturing association or by the industry. Set by association, like in this case ASME, or sometimes it's also set by industry. So sometimes maybe the association sets standards saying that something should be made with a tolerance of X, but the industry might have a standard that says it should be half of X. So it has a higher standard than what the association demands. And you might want to do that because maybe you want to distinguish your part from somebody else who doesn't quite make that good a part, right? And so then clearly in that case, if you have lower tolerances, then your part is going to be cheaper compared to something which has a more stringent tolerance. So then we have the codes. So these are specifications for the analysis, design, manufacture, and construction of a product. Okay, it sounds the same, but here's where the difference is. The difference is basically that standards are enforced by the association or industry, codes are enforced by the government. Okay, so it's set by local, state, or federal government. Okay, and so if they are set by the local, state, and federal government, then they carry the force of law. Which means that no matter what the standards are for a particular product, the company has to abide by the specific codes, because if not, there will be a lawsuit, right? And then that's not good. So then, if you go to the book, actually, it gives you a set of standards and codes relevant to mechanical engineers. I will not go through them, but see the book for list of standards and codes for mechanical engineers. So some examples would be if you, for standards, and we'll just go a quick check on this, standards, you will do a Google search for standards for ISO, which is the International Standards Office. and ASTM. And then for codes, let's do a quick search for ASME boiler and pressure vessel code. Okay, I just chose this at random. And ISO.org. So let's go to that website. Okay, so this is a pretty there are a lot of standards, and just choose something randomly. Okay, so these are the standards. Let's do the quality management standard, just something at random. Okay, so then if you go through that, you'll see that what the standard is. This basically dictates how important, how you quantify the quality of a particular product, right? And so if you go to one of these, it's basically going to try to get to a PDF, which basically gives you all the standards. Now, there's a lot of jargon here, which is probably not very interesting for us, but if you're in an industry which specifically looks at these standards, then it is. This is something which unfortunately you cannot view without buying it, right? So you probably, if you work in a company, they probably have access to this, they bought it and you can refer to it. But that's how you go and figure out a standard. And the same thing applies for the ASTM, that is, it's hidden from public view unless you pay a price. But what we'll do is for the code, we'll go to the ASME, we'll go to Wikipedia where they've put everything, boiler and pressure vessel code. And so if you go to the Wikipedia link, that's the ASME one, which again, if you go, then you'll see that there is a PDF which is under a paywall. Just put wiki. Okay, so that's how. All right, do this. Okay, there it is. Okay, so this gives you a lot about the history, but here are the rules about rules and regulations for this particular code by the ASME. So materials, rules for construction of nuclear facilities, how do you examine these things, and construction of pressure vessels. So you could go to one of them and then go through what the standards are. Actually, these UG 36, UG 48, 46, for example, are actually specific things in the document, which again is under probably under a paywall. But those are things which you need to go through if you are interested, for example, in openings and reinforcements. Okay. Anyway, there's a lot of information there, and probably it's not very important unless we actually come to the point where we're designing. So instead of trying to process that, what you would normally do is you'll make up, let's say that you're designing a boiler, right? And then the question you ask yourself is, what are the things involved in a boiler? What are the specifications? And then you'll go to the standards and see what the specifications are, and then try to meet them. Okay, so that's probably the way it's done. Nobody can possibly have like remember this, or you just have to know where to go and find the right information so that you can go ahead and do your job of designing something. Any questions? Okay, so let's move on to the next part, which I think is important, economics of the economics in basically design engineering. So economics. Okay. So no matter what you do, you want to ensure that you have a grasp over the economics of something. Maybe it is profitability, whether you're ensuring that you are able to break even with respect to setting up an industry and so on. So cost plays a very, very important role in design, right? And there are many aspects to it. We just talk about a few things here. So cost, what makes cost very interesting is that it really varies with location, material, and labor. Okay. maybe it's not best idea to open maybe a plant in Illinois. Maybe it's better to open a plant somewhere else where maybe the taxes are lower, or where it's much cheaper to procure material and so on. In a global economy these days, it's more cheaper to manufacture things in certain parts of the world rather than trying to manufacture everything in the US. And this is basically dictated by economics. Okay, so what we want to do when we talk about economics is we want to ensure that costs are reduced as much as possible. And what really helps in this case is having standardization. Okay, so when you're making a part, let's take the same automobile car example, right? Your tires on a SUV has a certain size, and you'll see the same size for almost all manufacturers in the US. And that's because by keeping the size the same, you only make a certain size for the tire and so on. And you may see one or two variations, but all of them would be, there won't be too many of them. There'll be a few of them. That way you can standardize and reduce the cost. So that's one part. The second part is that sizes are usually taken from catalogs, right? So if you want to make a new part and you want to come up with your own car, what you want to do is you want to choose a size from the catalogs. So for example, the catalog, and say that you want to make a different example, maybe a shaft, right, in your part. Now, your design calculations say that the shaft should be 53 millimeters. But if you look at the catalog, you may not find a part which is of 53 millimeters. It can be 50, 55, 60. So you got a choice there. You only want to use a part which is one of those three specifications, because if you want to make a 53 shaft diameter, then you'll have to machine it yourself. And if you machine it and if it breaks, then you cannot procure it from somewhere. You'll have to make it again. So by standardizing, you're ensuring that your parts are uniform, and that way you can keep the cost down. So the example is, if you need a 53 dia shaft, so you need to change your design to use either 50 or 55, because those sizes are in the catalog. That's one reason why I want standardization. So the other one is the availability. Okay, so maybe if you are 50 and 55, maybe it's possible that the part which is 50 is sold by more vendors than the one in 55. So it clearly makes sense to then go for 50 versus 55 maybe there are discounts for certain things, like 50 might be cheaper because it's made by many vendors. So that way you can bid and then you can get a discount. Okay, so this all applies when you are thinking of mass production. If you're thinking of making one product and you're not going to mass produce it, then maybe you don't have to go through this. Then we have tolerances. Now, when you make a shaft which is 50 millimeters, you see that when you measure it with a caliper, it will not be 50 It will probably be plus or minus something. So that plus or minus millimeters on the diameter is basically the tolerance on that particular product. So this is the dimensional tolerance. That is, you cannot have a perfect 50 millimeter shaft, no matter how hard you try, right? So for example, if you, as I said, you have a 50 and the way tolerance is written is plus or minus 5. So that's one type of shaft, say, which is made by some vendors, but you could also get another one, which is plus or minus 10 So it's very likely that this is costlier. It's more precise, clearly, but it's costlier. And that's because to go from to have that tolerance within plus or minus 5, you need to do 2 extra steps with your machinery, right? You need to sand it, file it maybe. And so it basically makes it more expensive. Okay, so this might be costlier. This is precise, cheaper, less precise. Okay, so in fact, the book gives this diagram, which I really like. It basically gives you a diagram of how the costs scale with the processing involved. Okay, so for example, this is for steel. Okay, and so this is the cost is on the y-axis and the tolerance is on the x-axis. So this basically tells you as you go from left to right, you can see that the tolerances are reducing. So this is 0.03, the units are inches. And then as you go down, you have 0.00025, which is extremely tight tolerance. Okay, so if you're using a machining operation like a lathe, then you just have to do rough turns to get to an accuracy of up to 0.005 inches or about 0.125 millimeters. But the moment you start going down from this range all the way down, you have to do semi-finished turn, finished turn, grinding, honing. And so those operations basically uh, involve either expertise, so you have to call somebody and make the person do it. The second thing, if it's done automatically, then there's a cost involved. The machine has to be running for that much time. And so as you go become more and more precise on the tolerances, you'll see that the cost invariably goes up. And so these parts definitely are, on the left side you'll have cheaper parts, and the right side you'll have more costlier or expensive parts. So cost increases as the tolerance decreases. Okay, so that is kind of important. Okay, so that gets us to this important thing is, and this is something which comes and will come often when you are thinking of a new product or investing in something. That is what is known as the break-even point. Okay, so break-even point. Okay, so we often hear break-even points in investment. Let's say that you're starting a shop which is going to sell something, and then there is a cost of setting up a shop, perhaps buying property. So that will be a fixed cost which you just pay up when you are basically buy that particular land, or maybe it's a lease. I don't know. Just depends on what industry you're in. And then that cost is a fixed cost. You have to bear it. But then as you start selling something, you basically start earning a profit. So as you earn profit, you can pay off the loan you took on the property. And eventually there's a point of time at which the costs which you paid upfront and your running costs are less compared to the amount of profit you're making. And that's when that point achieves, you basically have a break-even point, and after that you're only going to have profits, right? Ideally, you want to reach the break-even point as fast as possible. That way, you can start making a profit. Now, in case of design, you will have choices on what materials to use. You might use a lathe where you have to do manual machining, and you might have an automatic machine, and both of those will have different costs associated with them. So if you're given an order to make some part using a machine in your warehouse, then you could choose between one of the two, and you have to do this determination as to which of those options is the best option in terms of, maybe it could be monetary cost, it could be in terms of time, whatever is important for you. So the way I'll define break-even point is the point measured either as a cost, okay, as time, or basically cost or time, maybe cost, time, and quantity at which two processes have the same return. Okay, that is, if at that particular break-even point, before that reaching the break-even point, one of the machine would be, or one of the processes would be better than the other one, and past that break-even point, the other one would outscore over the other, over the first one. So here, let's look at an example of a problem related to break-even point. Okay, so there are two machines, A and B, that will be used to produce a niche product. A has a setup time of 5 hours, produce 20 parts per hour at the cost of $20 per hour. Okay, so let's just write that down. So A has a setup time of 5 hours. Okay, it produces 20 parts per hour, and it costs $20 per hour. Okay, so B, on the other hand, has no setup cost. Okay, it produces 10 parts per hour and costs $60 per hour. So let me just write that down first. Setup 0 hours. It produces 10 parts per hour and $60. Some of your writings, I'll just wait for a bit. Okay, so if you see this, just this numbers, you can see that A is taking more time upfront. You need 5 hours to set it up. But then as it actually produces 10 parts, so 20 parts, sorry, yeah, 20 parts per hour at $20 per hour. So it's producing more parts compared to B, right? And B also costs more per hour. So it's likely that A is some kind of an automated machine, and B is probably a manual machine, because the setup times are typically almost zero. Okay. Anyway, so that's not very important, but let's then try to find the break-even point. Okay, and when I say break-even point, I should have mentioned it in terms of quantity. Okay, there are actually two break-even points you can think of. One is, when do you break even in terms of time, and when do you break even in terms of quantity? So what is the number of products you need to, or number of parts you need to make on the machine, such that the cost for A and cost for B are the same? Okay, that's what we're trying to do. Okay, so what we need to do is basically write an equation for the cost as a function of quantity. Okay, so if cost is Y, quantity is X, we'll write an equation for machine A, and we'll write an equation for machine B, and then we would have the necessary tools in order to analyze and figure out the break-even point. Okay, so let's look at machine A. So for machine A, we have the cost as well. So we want in terms of quantity, right? So we see that there's a setup time of 5 hours. And in 5 hours, this machine would have produced 20 parts per hour. So, so it's basically in 5 hours, if that machine was in commission, was working, um, it would have basically cost us $100 to, or $100 worth of parts would have been produced if there was no cost for setting it up. Okay, so that is the time it takes for it to be up and running. So once it's 5 hours, after that, you'll see that it's actually producing parts. So in this case, it's producing 20 parts per, sorry, 20 parts per hour, and it's $20 uh, per hour is the running cost. So in this case, what we need to do is we need to find a ratio, a scaling factor, which when multiplied with the quantity gives us a cost. So this, whatever is here, has to have units of dollars per part. And so the way we can think of this is if you have 20 parts per hour at $20 per hour, you basically will have 20 divided by 20. So that's basically the slope. Or in general, it's just saying that you are going to basically incur, you're going to producing X parts in 1 hour would cost you 20 divided by 20 times X. So then this is 100 plus X. If you do the same thing for B, now the setup cost is 0. So the first part is 0. And then we would have $60 per hour. And then we would produce 10 parts per hour. So that times X would give us the amount of cost we need to pay to produce quantity X. So that's 6X. If you want to think of these in terms of a graph, then you would have a graph which is Y as a function of X, where Y is your cost and X is your quantity. So if you draw this line, the 6X line is probably simple. So let me draw that first. So this line Y equals 6S passes through the origin here, and then we'll just go, it'll have a slope of 6 divided by 1. So it'll be 6 on the Y, 1 on the X. So that is Y equals 6X. If you look at the other line, which is Y equals 100 plus X, it starts off, so when X is 0, we have 100. And then it basically has a slope of 1, right? It's because that coefficient in front of X is 1. So it will be like a 45-degree line, like this. Okay, so this point where the red line and the blue line being the line for A and the red line being the line for B, meet is called a break-even point. This is a break. Okay, and so we are interested in basically finding what that X is. So if you want to solve this, well, one is you can plot it on a graph and then look at the intersection. But the other way to solve it is you have two equations. Y is a function of X. When two lines intersect, then you can basically equate the two and then find the point of intersection. So we'll use that. Y equals 100 plus X should be the same as 6X, the second equation. So if you solve for X, you get, I think, 20. Right, so X is 20. That means that when you produce 20 parts is when you have a break-even point, and the cost for A versus B is the same. So you can, if you want, write this as a break-even cost. So the quantity is X is 20, and the cost for that is, now if you want to find the cost, one is you can put X in the first equation, which if you do, you'll get 100 plus X 20 is 120. If you put in the second equation, you'll get the same thing, 120. The cost is 120. Okay, so it's saying that if you are producing less than 20 parts, you want to go for B, right? If you're producing more than 20 parts, you need to go for A, because the costs for A in that case are lower compared to that of B. So that's your first part in the question. So break-even point, which is X equals 20. And then which machine will you use for 10 units and which one for 30 units? So clearly, if you want to make 10 units, then you'll use this one. So from the plot, we can see that for X equals 10, you'd probably use the red line, which is B. And the cost in this case is, if you look at the equation for B, it's Y equals 6 times X, which is 10. So it's 60. So you'll incur $60 to make 10 parts. Now, if you want to make 30 parts, in this case, 30 is going to be on the right side of the break-even point. So in this case, you'll be using the other machine. So it'll be A. In this case, the cost is X plus 100. So it's going to be 130. Okay, so that's the best you can do with the quantities you asked to manufacture. So that's how you do a break-even analysis to figure out the investment or the return on your investment. Okay, and so these are some of the important decisions you got to make when you are designing things, and as well as manufacturing and so on. Okay, so we have 5 more minutes. Let me talk briefly about safety and product liability. But any questions on that, economics? Okay, the last thing before we stop for today is safety and product liability. Okay, so the main thing you want to remember, and this is kind of important when you're making a product, is product liability is strict liability. This term is used to mean that, right? Let's say I'm the manufacturer of something, I make a part, and I put it in the market and it hurts somebody. Okay, if it hurts, it doesn't matter if I knew about the defect in the product or not. I will be sued. Okay, if I'm sued, then I have to pay. Okay, that's the strict liability. It doesn't matter what the manufacturer knows or doesn't know. You will be sued for it. So there are 3 things. So before I talk about how the liability works, the manufacturer in this case is responsible for any damage and harm from defective product. And that is no matter if he or she knew about it or not. Okay, so that's kind of what strict liability means. In this case, if there's a lawsuit, the there are three defects before that, three defects which can come up. One is the design defect. It could be a manufacturing defect. And third one, which is, and this is kind of important, is that failure to warn. Okay, so example would be, let's say that you make a helmet, okay, and the helmet is to be used in when you're riding a bike, okay, but somebody uses the helmet on something else like skateboarding, and the person hurts himself or herself. So if the manufacturer of the helmet said exclusively that this helmet is to be used for riding bikes and not, you just say that much, then using that on a skateboard cannot be used as a case for suing the company, because it exclusively said that this helmet has to be used on a bike and not on a skateboard. So failure to warn is one of the most important thing, and that's why when you open a product, you see that there will be a warning label telling you what that product can be used for not. Okay, so in this case, if you have a lawsuit, all the thing that the plaintiff has to prove is, one, is show that the article was defective, or two, show that article caused harm. Okay, that's all. It doesn't matter if so if I put a helmet out, as I said, and did not have that notice on that about where it can be used, then I can be sued. So what manufacturers do in this case to avoid being sued, you want to ensure that you have a good design. Okay. So when you make multiple designs, you test them out. You have good materials, right? You probably want to follow the standards and codes, because if you don't follow them, then that's immediate lawsuit because you did not follow a particular protocol. You want good quality control. Okay, before you roll out a part, you need to test it out. And then the last thing is, well, good testing protocols. And the final thing is warnings, right? Tell people what it can be used for and what cannot be used for. Okay, so it's